Are we alone? I mean, it is without a doubt the ultimate question. It's the one humanity has been asking itself since, I don't know, the first time someone huddled around a fire, looked up at all those stars, and realized they weren't just pinpricks of light, that they were actual places.
Other suns, other worlds.
Exactly. And for centuries, millennia even, the answer has just been silence.
Right.
Just a whole lot of empty static from the universe. But very recently, the James Webb Space Telescope, the JWST, might have just changed everything. We could be talking about the end of the Are We Alone era.
It is certainly one of the most compelling developments in exoplanetary science we've seen in years. And we're looking at data from a world called K2-18b. Now, we need to be very, very careful with our language today. And I'm going to be the one pumping the brakes for this deep dive.
I know. The voice of reason.
But even with that caution, the findings are, to put it mildly, provocative. We are really standing on the precipice of a shift in how we understand our place in the cosmos.
Provocative is a polite way of putting it. I mean, I want to jump right into the deep end here because the headlines, they aren't just whispering, they're screaming aliens. We're not just talking about finding some water or, a nice temperature where you could get a tan.
No, this is much more specific.
We're talking about a specific molecule that has been detected in the atmosphere of this distant world. A smoking gun, if you will. It's called dimethyl sulfide, DMS. And when I saw this news, I literally, stopped scrolling and just said, wait, seriously?
Correct. DMS.
Wow.
It's a small molecule, chemically speaking, but it carries a very, very heavy implication.
And here's the kicker, and the reason we're doing this deep dive today. On our planet, on Earth, DMS is only produced by one thing: life. Specifically life in our oceans. So let's unpack this immediately. Did we just find life on K2-18b? Is this it? Is this the moment where history splits into before and after?
Well, that is the question of the hour, isn't it? But before we break out the champagne or, prepare a welcoming committee, we have to look at the context. This isn't a scene from a sci-fi movie where a saucer lands on the White House lawn and a ramp comes down.
Right. No little green men.
Not at all. This is a story about chemistry. It's about atmosphere. And about the very definition of what a habitable world can even look like. It's a detective story where the clues are photons of light that have traveled for 120 years just to reach us.
Okay, right. And that's our mission for this deep dive. We're going to explore these echoes of life on K2-18b. We need to really understand what this planet actually is because, spoiler alert for all of you listening, it looks absolutely nothing like Earth.
Not even close.
We need to understand this Hycean world concept, which is a total mind-bender on its own. And we've got to get into the nitty-gritty of these biosignatures. Why is DMS such a big deal? And why are you, my voice of reason, looking at me with that classic calm down expression?
Because my role here is to balance your, let's call it, scientific wonder.
I'll take it.
With a healthy dose of academic analysis. We're walking a tightrope today. On one side is potentially the most groundbreaking discovery in human history, the confirmation that biology is not unique to Earth. But on the other side is the rigorous, absolute need for data and the elimination of all error. If we're going to claim we found life, we better be absolutely 100% sure.
Okay. I can handle the tightrope, especially if there might be aliens on the other side. So let's start with the stage itself. We keep saying K2-18b. It sounds like, I don't know, a droid from Star Wars or a tax form.
It's not the most poetic name, I'll grant you.
But it's an exoplanet. For everyone listening who might need a quick refresher on that, what exactly does exoplanet imply in this context?
Simply put, an exoplanet is any planet that orbits a star outside of our own solar system. It seems like a basic definition, but the implication there is really about distance and isolation. We aren't talking about Mars or Venus, which are essentially our next-door neighbors in the cosmic suburbs.
Right, we could, in theory, get there.
We can get there. It takes a while.
Yeah.
But it's feasible. We're talking about a world that is roughly 120 light years away.
120 light years.
Yeah.
In sci-fi, that's like a commercial break. But in reality, that's just an incomprehensible distance, isn't it?
It is, truly. To give you and your listeners a sense of scale, light travels at about 186,000 miles per second. It takes light from our sun 8 minutes to reach Earth.
8 minutes.
8 minutes.
Yeah.
It takes that same light 120 years to get from K2-18b's star to us. If we sent our fastest current spacecraft, say the Parker Solar Probe, which moves incredibly fast, it would still take hundreds of thousands of years to get there.
Hundreds of thousands. Wow.
So, in a way, we're looking at a ghost. We're seeing the planet as it was 120 years ago, back in the early 1900s on Earth.
So we can't exactly, send a drone over to take some pictures. We aren't going to see a rover rolling around on the surface sending back selfies anytime soon.
Exactly. We cannot resolve the surface. We can't see continents or clouds in a photograph like we can with Earth or even Jupiter. To our telescopes, even the absolute best ones like JWST, K2-18b, it's a point of data. A single flickery pixel.
On pixel.
Everything we know, everything we're going to talk about today comes from analyzing the light from its star after it passes through the planet's atmosphere. But what makes K2-18b so special isn't just that it's an exoplanet, it's where it sits relative to its star. It resides in what we call the habitable zone.
Ah, the famous Goldilocks zone. Not too hot, not too cold.
Precisely. The habitable zone is the region around a star where the conditions are theoretically just right for liquid water to exist on the surface. If you're too close to the star,
Air toast.
you're toast, like Mercury is to our sun. Any water just boils away into steam and escapes into space. It's an inferno. If you're too far out, like Pluto, everything freezes into rock-hard ice. K2-18b sits right in that sweet spot where liquid water is at least possible.
But that zone, it's not the same for every star, is it? Like a smaller, cooler star would have its Goldilocks zone much closer in.
That's a great point, and it's key to understanding this system. It's entirely dependent on the star. K2-18b orbits a red dwarf star, which is much, much cooler and dimmer than our sun.
Okay.
So its habitable zone is much more compact. It's huddled closer to the star. The planet is actually orbiting very close to its star, much closer than Mercury orbits our sun, but because the star is so cool, it's still in that perfect temperate zone.
Okay, so we have a planet that isn't burning up and isn't a frozen wasteland. It's in the sweet spot. So naturally, my brain immediately pictures Earth 2.0. Blue skies, green trees, maybe some beaches, a nice breeze. But looking at the research here, that is, well, it's not accurate at all, is it? We tend to project Earth onto everything we find out there.
That's a very human bias and a very persistent one in this field. But no, it is not accurate, not even close. This is where our imagination really needs to stretch a bit. K2-18b is what astronomers have started calling a Hycean world. And this is a very, very new concept in astronomy. It forces us to rethink what a planet can even be.
Hycean. I love that word. It sounds like something from a high fantasy novel, The Lost Kingdom of Hyceia. But it's actually a portmanteau, right? Just two words smashed together.
It is a very elegant one. It combines hydrogen and ocean. Hydrogen plus ocean equals Hycean.
So break that down for us. What does a Hycean world actually look like? If I could just teleport there and, assuming I didn't die instantly, what would I experience?
Well, first, you'd feel incredibly heavy. It's a much bigger planet than Earth, about 2.6 times the radius and around 8.6 times the mass. Gravity there would be intense. It's what we call a sub-Neptune or a mini-Neptune.
Okay, so it's sort of a failed gas giant.
You can think of it that way. It's in that gray area between a large, rocky super-Earth and a small, gassy planet like Neptune. But the real difference is the composition. Unlike Earth, which has a relatively thin nitrogen-oxygen atmosphere like the skin on an apple, really a Hycean world is blanketed in a thick, massive atmosphere that's rich in hydrogen.
A hydrogen sky. That implies a completely different color, doesn't it? A different way light scatters and looks.
It absolutely does. It likely wouldn't be the familiar azure blue we're used to. It might be reddish or pale, depending on the other trace gases. But the ocean part of Hycean is even more fascinating. Beneath that crushing, thick hydrogen atmosphere lurks a surface that is likely covered entirely by a global ocean.
Wait, entirely? Like Waterworld the movie, no continents?
Potentially. No continents, no islands, just water, possibly hundreds or even thousands of kilometers deep. On Earth, our oceans are just this thin, damp layer on top of rock. The deepest trench, the Mariana Trench, is about 11 kilometers deep. On a Hycean world, the water is a dominant feature of the planet's very structure. And given the atmospheric pressure, there would be a hot, high-pressure ocean. Not necessarily boiling, but very, very warm.
That's terrifying and beautiful at the same time. I'm picturing this dark, planet-wide ocean under a heavy, maybe reddish hydrogen sky. It really challenges our whole perception of what a living world is supposed to look like.
It does.
We're so biased towards Earth-like conditions. We want rocky ground to build cities on. We want forests. But this suggests that life might have a completely different kind of stage to play on.
And that's a crucial point that's changing the whole field of astrobiology. For a long, long time, the search for life focused almost exclusively on finding Earth twins. Rocky planets, similar size, similar air. But the Hycean hypothesis opens up a huge, huge new demographic of planets to search.
Because these worlds are more common.
They seem to be, yes. These sub-Neptunes are actually quite common in the galaxy,
Right.
potentially more common than Earth-like planets are. So if they can support life, then the universe might be far more crowded than we thought, just not in the way we expected.
So, okay, we have the stage. A massive water world, K2-18b, floating in the Goldilocks zone, 120 light years away. It's a mini Neptune with a surface. Now let's talk about the actor on that stage, the ghost in the machine. We mentioned DMS, dimethyl sulfide. This is the echo of life we're hunting.
Right. And this brings us to the concept of a biosignature. This is a fundamental term in astrobiology that you and the listeners really need to grasp to understand the news.
Right. Okay, so break it down for us. What's a biosignature?
When we look for life at these immense distances, we aren't looking for the life itself. We can't see an alien waving at us.
Oh.
We can't see cities or forests. We are looking for the chemical byproduct of life's metabolism. We're looking for a biosignature, a gas or a molecule in the atmosphere that shouldn't be there unless something living is constantly pumping it out. It's not seeing the fire, it's smelling the smoke.
I like that analogy. Or like walking down a beach and seeing a footprint in the sand. You don't see the person, but the shape of the indentation tells you someone walked there. Or finding a candy wrapper on the ground in a forest. The wrapper isn't the person, but you know a person dropped the wrapper.
That's a perfect analogy, exactly. And DMS is a very, very specific shape of footprint. It's a very specific brand of candy wrapper.
Okay, so here is where it gets really interesting for me. Because when I read about DMS in the source material, my mind was just blown. On Earth, this stuff isn't just common, it's incredibly specific.
It is. Dimethyl sulphide is what's called an organosulfur compound. And on our planet, the vast, vast majority of DMS in the atmosphere comes from one source and one source only: life, specifically marine life.
Marine life. So we're talking about the ocean.
Precisely. It's produced primarily by phytoplankton in the oceans.
Phytoplankton, the microscopic algae floating in the sea. The stuff that's at the very, very bottom of the food chain.
Correct. When phytoplankton are eaten by other tiny creatures called zooplankton, or when they just die and decay, they release a precursor chemical that then breaks down into DMS. Now, DMS itself breaks down very rapidly in the atmosphere due to sunlight, so if you find it, it means something is constantly replenishing this supply.
It's not just some old gas hanging around from a billion years ago.
Absolutely not. It has a short shelf life. And it's actually what gives the ocean that distinctive seaside smell. If you've ever stood on a coast and smelled that pungent, salty, slightly cabbage-like biological scent, that's DMS you're smelling.
So the smell of the beach is the smell of life, that rotting kelp smell.
Biologically speaking, yes. That's the smell of a massive, ongoing biological process. And here is the absolute key to this entire discussion. There are no known significant geological or chemical processes, what we call abiotic processes, that produce DMS in the quantities needed to be detected on a planet like Earth or K2-18b without the involvement of biology.
So volcanoes don't make it?
Oh.
Lightning strikes don't make it?
No, rocks don't just, exhale DMS. On Earth, the biological production outstrips any potential non-biological source by orders of magnitude.
That is the smoking gun. I mean, come on. If K2-18b is a Hycean world, meaning it's covered in water, and we detect a molecule that on Earth is only made by little critters living in water, I mean, the connection is incredibly, incredibly strong. It feels like 1 + 1 = aliens. It just seems almost too perfect.
It is an incredibly compelling narrative. You have a water world, and you find a molecule that's strongly associated with water-based life on Earth. The logic holds together beautifully. The environmental context matches the biological context that we know. It's not like finding a desert gas on an ocean world. The pieces fit.
And we found this using the James Webb Space Telescope. Can we just take a second here to appreciate the tech involved? Because this isn't just a big magnifying glass pointed at the sky.
The engineering is just staggering. JWST didn't just take a picture. It performed something called transmission spectroscopy.
Spectroscopy, that's separating light into a rainbow, basically, right?
That's the core idea. When K2-18b passes in front of its star from our perspective, an event we call a transit, the starlight has a filter through the very edge of the planet's atmosphere on its way to us.
Okay, I'm picturing that.
Think of the planet's atmosphere like a stained glass window. Different gases in the atmosphere absorb very specific colors or wavelengths of light. So by analyzing which colors are missing from the starlight when it finally hits the telescope's mirror, JWST can tell us what gases are floating around in that atmosphere 120 light years away. It's like reading a chemical barcode.
A chemical barcode, I like that.
Precisely. And in that barcode, it clearly detected methane and carbon dioxide, which helped confirm the idea that it has a hydrogen-rich atmosphere. And then, more faintly in the data, it picked up the potential signature of DMS.
It's like spotting a specific grain of sand on a beach from a mile away.
It's maybe more like standing in New York and analyzing the chemical composition of a single puff of smoke in Los Angeles that's floating next to a giant spotlight. The precision required is it's unbelievable. The fact that we can do this at all is an absolute triumph of human ingenuity.
Okay, so we have the stage, the Hycean world, we have the evidence, the DMS footprint. I am ready to declare victory. I'm ready to say we found them, but I can see you shifting in your seat over there. You're pulling back.
Yeah.
Why? What's the catch?
The catch is scientific skepticism. And I don't mean skepticism in a negative way, like, oh, I don't believe you. I mean it in the sense of absolute scientific rigor. The source material for our deep dive today emphasizes this very conflict, discovery versus skepticism.
We've been burned before.
Burned before? What do you mean?
Well, think about the phosphine on Venus controversy from a few years ago. It was a very similar story. A molecule, phosphine, was detected in the Venusian clouds. On Earth, phosphine is associated with anaerobic life that doesn't use oxygen.
Right, I remember that. The headlines were huge. They were. Life in the clouds of Venus. But then other teams looked at the data, reanalyzed it, and the signal was much weaker than first thought. Some argued it could be a data processing error. Others proposed exotic, non-biological chemical pathways in the unique Venusian environment that might create it. The consensus now is that it's very unlikely to be life.
But the DMS, we just said only life makes it.
On Earth. Only like we know of makes it on Earth. We're dealing with a completely alien environment, a hydrogen-rich atmosphere, likely at temperatures and pressures we don't fully understand. We don't have a planet like K2-18b in our own solar system to use as a laboratory. So is it possible there is some exotic photochemistry happening in that upper atmosphere, some reaction we've never seen before, that creates DMS without life?
So nature might be tricking us.
Nature is fantastic at tricking us. We have to be incredibly careful about false positives. Just because we haven't yet figured out a non-biological way to make DMS under those specific conditions doesn't mean one doesn't exist. Maybe high-pressure hydrogen reacting with sulfur compounds from the planet's interior creates it? We just don't know yet, because we haven't been able to model it perfectly.
Ugh, that's so frustrating. I want the answer to be yes.
I think we all do.
Yeah.
But science isn't about what we want. It's about what we can prove. And there's another point. The signal for DMS in the JWST data was also, it wasn't as strong as the signals for methane or carbon dioxide. The scientists who published the paper were very, very responsible about this. They stated that the presence of DMS is detected with low confidence compared to the other gases.
Low confidence. That is just a buzzkill phrase right there. It sounds like a bad weather forecast. Low confidence of rain today.
It's an honest phrase. And in science, honesty is everything. It means the data is suggestive, it's a tantalizing hint, but it is not definitive. It's a lead, not a verdict. We need more data. We need to point JWST at this planet again, maybe for longer periods, to separate the signal from the background noise. Science requires reproducibility.
So we have these two perspectives basically battling it out. Perspective A, which is where I'm sitting, this is a groundbreaking discovery. We have a water world and the smell of life. This could change history. And then there's perspective B, your side. Caution, rigor. We can't jump to conclusions because the universe is complex and could have chemistry we haven't even dreamed of yet.
And both of those perspectives are absolutely necessary for good science. Without your wonder, we wouldn't bother building the telescope in the first place. We wouldn't spend billions of dollars to look at a single speck of light. But without my caution, we'd announce aliens every time a cloud passed in front of a star, and we'd lose all credibility.
It's the ultimate balance. Scientific wonder meets academic analysis.
Precisely. And honestly, for me, even the possibility is enough to justify the excitement, even if it turns out not to be life. Just studying a Hycean world in this detail teaches us so much about how planets form and evolve. If it's not life creating the DMS, then it's a new kind of planetary chemistry we've never seen before. That, in itself, is also a huge win for science.
That's a good pivot because to really get why this all matters, we have to understand the language we're using. The source material talks about a linguistic journey. And I find this fascinating because the words we use really do shape how we think about the universe, don't they?
They absolutely do. It's not just about grammar or vocabulary. It's about having the right tools to describe reality. Think about the words we've been using today. Exoplanet, habitable zone, biosignatures, Hycean.
Hycean is definitely my new favorite word. It just sounds so ancient and cool.
These aren't just jargon, they're conceptual tools. 20 years ago, the word Hycean didn't exist in this context. We didn't have the language to describe a hydrogen ocean world because we didn't really know they could exist in this way. We thought planets were either rocky like Earth or gas giants like Jupiter, with nothing much in between.
So as we discover new kinds of things, we have to invent new language to contain those ideas.
Exactly. And look at a word we take for granted, like atmosphere. In normal conversation, atmosphere is just the air we breathe, or maybe it's the vibe of a restaurant.
Right, this place has a great atmosphere.
But in exoplanetary science, the atmosphere is the storyteller. It's the history book of the planet. By reading the chemical composition, the methane, the CO2, the potential DMS, we are reading the biography of the world that lies beneath.
That's a beautiful way to put it. The atmosphere is the biography of the planet.
It is. It tells us about the geology of the interior, the nature of the surface, the overall temperature, and, yes, potentially the biology. And you can see how our language about space has evolved over time. We used to talk about little green men or Martians. Those are terms rooted in fiction and, frankly, a bit of fear.
Yeah, very sci-fi B-movie.
Exactly. Now we talk about hunting for DMS and analyzing spectra for biosignatures. We've moved from these science fiction tropes to specific, quantifiable chemistry.
It's less take me to your leader and more show me your molecular structure.
Which, admittedly, is less cinematic. You're probably not going to get a summer blockbuster out of a movie called The Search for Dimethyl Sulphide, but it is far, far more profound. If you don't understand what Hycean means, that specific combination of a hydrogen sky and a water surface, then you can't understand why the phytoplankton connection is so relevant. You have to speak the language to grasp the magnitude of the news.
Right, it empowers us to understand the headlines. So instead of just seeing a headline that says aliens found, we can see one that says potential biosignature detected on Hycean world and understand the nuance. And that nuance is everything.
It matters immensely because the truth almost always is in the nuance.
So let's zoom out. What does this all mean? We've looked at the chemistry, we've looked at the data, the vocabulary, but let's get a little philosophical for a minute because the source material nudges us this way. If K2-18b really does have life, even if it's just, slime, even if it's just microscopic phytoplankton floating in a dark, warm, deep ocean, what does that do to us? What does that do to the human story?
It shatters the silence.
The silence.
The great silence we talked about at the very beginning.
Yeah.
For all of human history, we've shouted into the cosmos, is anybody out there? And heard nothing back. If we find life on K2-18b, it implies that the emergence of life isn't some 1 in a trillion miracle that happened just once on Earth. It implies that life is a natural, perhaps even common consequence of the laws of physics and chemistry.
If it happened here and it happened there,
then it's probably happening everywhere. If life can emerge on a rocky nitrogen atmosphere world like Earth A and D, on a massive hydrogen atmosphere Hycean world like K2-18b, then life is far more robust than we thought. It's more adaptable. It suggests the universe is just teeming with it. We go from being a lonely anomaly to being part of a very crowded room.
And it connects us to them, doesn't it? I mean, I can't stop thinking about the phytoplankton on Earth. They're these tiny, fragile, invisible things, but they're crucial to our entire food chain. They produce a huge amount of the oxygen we breathe. And to think that across 120 light years of empty void, on a totally different kind of planet, there might be something similar doing the exact same thing, producing the same gas.
It suggests a certain universality to biology. It suggests that while the shapes of life might be wildly different, the aliens might not look anything like us, the underlying chemistry of life, that fundamental drive to consume energy and produce byproducts, might be constant across the cosmos. It bridges the gap between us and the stars. It means we aren't a fluke.
It makes the universe feel a little less cold and empty.
And a whole lot more interesting. It turns the night sky from a map of physics into a map of biology.
It really does. Wow. So let's try and wrap this up. We have covered a massive amount of ground or space, I should say, today.
We certainly have. We've gone from the basic definition of an exoplanet all the way to the philosophy of existence.
So let's recap the key takeaways for everyone listening. First, the James Webb Space Telescope turned its incredible golden eye toward K2-18b.
A world 120 light years away. A mere stone's throw in cosmic terms, but an impossible gulf for us.
Second, we learned that K2-18b is a Hycean world. This is not Earth 2.0. It's a massive planet with a hydrogen-rich atmosphere and potentially a global ocean, a totally different type of habitable environment.
A distinct and fascinating new class of planet that forces us to broaden our search parameters for life beyond just Earth clones.
Third, and this is the big headline grabber, they found traces of DMS, dimethyl sulfide, a molecule that, at least here on our home turf, is the signature scent of marine life.
Produced specifically by phytoplankton. A very, very compelling potential biosignature.
And finally, the big caveat, the voice of scientific skepticism. It's a promising lead, it's a strong hint, but it is not yet definitive proof. We need more data, more observations to rule out any and all other possibilities.
Which is exactly how good science works. It's a slow, methodical, sometimes frustrating march toward the truth. We have to verify before we can canonize this discovery.
But man, what a truth it might be. I want to leave all of you listening with a thought. The source material asked us to consider humanity's place in the universe. And I think this discovery, or potential discovery, really forces us to look in the mirror.
Go on.
Well, we spend so much time looking up, wondering if anyone is looking back at us. But if K2-18b has life, and if that life is just simple algae floating in a deep, dark ocean, they don't know we're here. They aren't looking for us. They don't have telescopes or radios. We are the observers.
For now, at least. We are the part of the universe that is waking up. We are the universe becoming conscious of itself.
Exactly. So here's the final question for you to mull over. Are we the observers of a crowded room, finally noticing we're not alone? Or are we just seeing our own reflection in the data? Are we projecting our desperate human need for company onto a faint chemical readout from a world we'll never touch? Or have we finally actually found a neighbor?
That is the question that will drive the next decade of astronomy.
Mm.
And regardless of the final answer, the search itself defines us.
And I, for one, can't wait to see what we find. Thanks for taking this deep dive with us.
It has been an absolute pleasure.
Keep looking up.